Hello, my name is Morten Skov. I'll present our tool paper AalWiNes, which performs fast and quantitative analysis of MPLS networks. The operation of MPLS networks is an error-prone task, and it is in particular hard to reason about the behavior of the network in case of failures. Past work has focused on logical properties like reachability and waypointing. However, the quantitative aspects, such as latency and hop count in the trace, can also be important to look at. Today we present a tool that for data plane verification of MPLS networks, where we also take into consideration the behavior of the network when fast reroute kicks in case of possibly multiple failures. Our tool uses an over-approximating construction for which there is a polynomial time algorithm to solve the verification task. We take a first step towards verifying quantitative aspects, and we provide a graphical user interface for our verification tool. Let's take a look at an example of a network topology and a routing table in our model. Here a packet with an IP header enters the network at E0, and the routing table, we have two entries for this case. We non-deterministically pick one of them. This is how we model, for example, ECMP and load balancing with non-determinism. At the next router we have again two entries, but we pick the one with the lowest priority. We swap the label, and at the next router we pop the label, and the packet exits the network at E7 with an IP header only. This is one possible trace through the network. Consider instead the case where there is a link failure on the link E4. Here we need to take the second priority routing entry. We push the label 30 on the MPLS header. This encodes the fast reroute path that provides local protection for E4. This is a different path through the network, and indeed there are several traces in the network. Our tool provides a query language with regular expressions on the initial header, the links, and the final header in order to specify what kind of traces we're looking for in the network. The number k specifies the maximum number of link failures that we'll consider. As an example of a property in this query language, we here have a reachability query, which asks for reachability from the router v0 to v3, with initial final headers just IP. We can extend this to waypointing, where we ask if we can also go through v4. If there are no failures in the network, this is actually not the case in this example. However, as you saw before, if we allow one failure, there is a trace to satisfy the waypointing query. We can also use negation in the regular expression to avoid certain edges, and we can ask questions about the header, such as here, is there more than one MPLS label when we leave the network? As we saw, there can be multiple traces which satisfy a given query. In this case, we want to find a witness trace that minimizes some quantitative property, because these traces can have different quantitative aspects. The property we look at is the number of hops, the latency based on some predefined value for each link, the number of failures that's needed in the network for this trace to be present, and the number of push operations, also called tunnels here. We can combine these properties in a linear combination, and we can also put them in an ordered vector where we use lexicographical ordering for comparing. In this example, we first minimize the number of hops, and if that is equal for two traces, for example, we then minimize this expression with failures and tunnels. Our tool works by translating the regular expressions in the query into a finite automata, and the MPLS network is naturally modeled as a push-down automata with these push, pop, and swap operations. These are then combined into another push-down automata, where the query satisfiability problem is simply reachability in the push-down automata. This problem has a polynomial time algorithm to solve it, and we compute the witness trace if there is one. In order to handle link failures, we need to use an over-approximation. Here we consider each router independently and look at the routing tables or the routing entries that are active if at most k links fail. Then when we get a witness trace, we need to check if it is indeed valid, because we use this over-approximation. And in a few cases, our tool is inconclusive. Our implementation is open source on GitHub, and we also have an online demo of the GUI. Here we can load in a model, which I've already done here, and we can specify a query like this simple reachability query, and we can specify what quantitative aspect we want to minimize. When we run the tool, we can see that this query is indeed satisfied, and we get a witness trace that we can step through like this in the graphical user interface. This diagram gives a bit more detail into the construction. In particular, we use an under approximation in case the over approximation fails to be conclusive in more cases. We call this combined approach dual in our experiments. We also implement our own solver for push-down reachability, and we compare to an existing state-of-the-art solver for this problem called Moped. For the performance evaluation, we first look at a real-world network and some queries that the network operator requested. We can see in the column dual that we are faster, this is in seconds, faster than the Moped tool with our implementation. And when we look at minimizing the quantity failures, there is only an acceptable overhead compared to the dual column. We also perform a bunch of experiments on synthetic networks, and we see similar trends in the performance here. We can actually see that minimizing number of failures is inconclusive in fewer cases than this dual approach. For more details on our experiments and future directions, please refer to the paper. Thank you very much.